Hello guys, my name is Ahmed Abdel Fattah. I study biomedical engineering at the University of Kent. I'm going to be talking about my 4-bar mechanism. This 4-bar mechanism, I tried my best with it. I didn't use the best material. Used out of plastic, something similar to plastic, kind of hard to make it. And I did make a mistake with the sliding shaft. So this is supposed to be a fixed point, and this is supposed to be a fixed, and this is supposed to be the sliding point. However, I did it kind of the opposite, where this is the sliding point. Obviously, you can put it. This is not how it's supposed to be. It's supposed to be the opposite, where this point moves towards this direction. So actually, it becomes like this. So I messed up with it I wasn't really. I lost focus, and this is what I came up with. Obviously, I'll use a diagram to explain it further, but this is what I came up with. Just one mistake. Again, I'm going to repeat it. So this is supposed to be the sliding point, moves in this direction. This is supposed to be the fixed point. For me, it's opposite. Now I'm going to be talking about the physical therapy intention behind this mechanism, 4-bar mechanism. The physical therapy aims to improve the range of motion and strength of the elbow, since we're working with the radial head neck fracture. The therapy will focus on controlled movements to avoid over-exertion, and it obviously ensures afterwards a safe rehabilitation process. As for designing the 4-bar mechanism, the 4-bar mechanism obviously will be used to facilitate controlled flexion. So when you slide this, flexion and then extension of the elbow, it will simulate the movement of the forearm, allowing the patient to perform rehabilitation, as I said, exercises safely. Now I'm going to be moving, obviously I'm going to talk about the mathematical part later, but why is it important? The mathematical analysis, why is it important? And it's important, obviously, it's crucial to ensure a natural and safe movement for the patient. The lengths of the fixed links and forearm link, as well as the positions of the rotating joints, it needs to be calculated and in order to achieve a desired range of motion. During the calculations, obviously we're going to have trigonometric principles. We're going to be using geometric and trigonometric principles, and this will help us determine the appropriate appropriate link lengths to simulate the elbow joint movement accurately, and this will help us set the resistance mechanism to control the amount of force required during the therapy. And I think that's going to be towards the end, where obviously we calculate the velocity, the angular velocity, and then obviously with the velocity you got the acceleration that happens later. So we have the reference system over here, the X and Y reference system. Basically, if you move counterclockwise, it gets positive. We have the diagram over here that I'm going to be talking about briefly. Obviously, we have the horizontal line, x-axis, we have the vertical line, and we have the hypotenuse with theta 3, theta 1, theta 2. I've named it R2 as for this side, R2, R3, R1. Now, we have obviously the horizontal, I said, the vertical, the hypotenuse, and this is going to help us find the amplitude of the angle without the need of calculations. You can use trigonometry in this case. The angle, as you can see here, theta 3, in between the fixed length and the vertical side. This angle will be dependent on the patient himself or herself. Basically, whatever is the patient's movement is, that's gonna be dependent on him. The angle is gonna change depending on him. Now we know that the vertical side is the same direction as the y-axis, and the horizontal side is the same angle as the x-axis. Now using trigonometry with this sense, first of all, I forgot to mention, we need to remember that in this is basically an image, so it's like a frozen image. So we have the fixed points obviously, and we have this angle theta that's going to be changing. So when you move, since I can't show you with this one, so you move this in this direction, you move in this direction, theta will change, theta 3. Now, yeah, back to it, is that using trigonometry, we know that theta 1, obviously since it's a right triangle, it's going to be 90 degrees, and we know cosine 90, whatever. So after finding, so theta 1 would be 90 degrees, and you have theta 2, it would be 0 degrees. In this case, theta 3 would be arbitrary, constant. Moving on to the calculation part, we have, since we know it's an image, we know that the fixed points, since it's not moving, since it's at equilibrium, the fixed points need to balance, basically the forces need to balance out for it to not move, so it would be equal to 0, which means that R1, R2, R3, adding them, summing them all together would give us 0. That's how we got this here. In order for this to not move, so it would make sense that all of these at equilibrium would equal to 0. That's why you have the fixed points. They make sure that this thing holds together and it's equal to 0. As we studied, we know that we have to find the x components. We have to find the y components, which is over here, using trigonometry. So after finding the x components, y components, you substitute the angles that we have. We come up with these over here. So we need to use this to find R2, since we can get R3 since it's a fixed point. We get theta 3 since it's arbitrary. We don't need this second one since, oh yeah, by the way, we got these by substituting cosine theta 2, whatever. This is what we got, this is the aftermath. We solve for R2, we move R3 cosine theta, whatever, to the other side. We solve for R2, we find R2. We don't need the second one because we have R1, R3, it's not needed since it's already known. After we solve for R2, we can actually find the velocity of the sides that we have. Obviously using the same equation, derivative. After we find the velocity, by the way, here we don't find the velocity for R3 since the linear velocity is equal to 0 because it's a fixed point. So we find V1, V2, find those angles, and after that you differentiate it further, and you can find the acceleration for both A1, A2. I think this is it. Sorry for this badly designed, made a mistake. Again, this is supposed to be a sliding shaft. This is supposed to move in this direction. You know it's more than me. This is it. This is my design. Thank you so much.